Okay, now I'd like to talk to you about like service mesh at scale, and not just small or medium scale, but giant scale. The problems that service meshes are designed to solve, of secure, connect, observe, are as important in bigger and bigger companies as they are in smaller deployments. And so service meshes, we need them to scale out to, well, some of the largest deployments on Earth. We've obviously got a lot of experience building and deploying sidecar service meshes for many years now, and talked a little bit about some of the architectural limitations, right, that we see in the sidecar model. Because the sidecar model, and we deploy proxies with every unit of the application, it creates a lot of pressure on the control plane to deliver configuration to the sidecar. Because the sidecar needs to be able to route across very, very broad topologies, it needs to see a lot of information about the systems and the endpoints that are in the network and even across network boundaries. And the way that we achieved that in the sidecar model in Service Mesh today was to have any single instance of the control plane view and observe all of the services and endpoints for anything the sidecar could ever possibly talk to. And that meant if there were 100 clusters, then a single instance of the service mesh control plane would read the configuration discovery information out of 100 Kubernetes API servers. That creates a whole bunch of operational issues that really start to put a lot of pressure on the control plane. And because the amount of configuration state that we have to shunt down to the sidecar is quite large, there's also a lot of bandwidth coming out of the control plane, and the whole system at a certain limit really starts to kind of fall over around that kind of 50 to 100 cluster scale. And depending on how many pods and services are, that scale actually comes down into the kind of tens of clusters. And yet, if we look at what we see in the world today, we have customers and people we work with who are running thousands of clusters. And so we need a system that's going to work at that kind of scale. And so we've done a lot of work here at Solo to build a multi-cluster solution that will scale up to that kind of size. And we recently published a blog post where we did a test on an ambient mesh that contained 100 million pods and was running on over 5,000 clusters, right? So we're now really talking about like some of the largest possible deployments on Earth. So we've proven that we can make ambient mesh work for that environment. And I'm not going to talk about all the architectural details. You can read about those in the blog post that we'll link to. But given that we have a system that can now scale out to massively multi-cluster environments, what do you want to do with that? What are the kinds of patterns that you want to use? Obviously, having something running at that scale allows people to, regardless of their scale or their topology even, or where these things run, because the system doesn't really care, we can now have a global system of policy record for the entire application universe running in some of these giant environments. And that in and of itself is a massive value, in addition to the kind of secure, connect, and observe features that we provide. So we see a couple of patterns that in really, really large multi-cluster environments, you don't want every cluster to talk to every other cluster. That's not actually what you want. And so there's a kind of few fundamental patterns that we see. Probably the first of which, and one we see, is the kind of global ingress problem, right? So I have clusters, and these clusters are regional, and I may have a fairly small number of them, and they basically represent the points of presence for my public services, right? So these are running ingress proxies, and then inside the network, we have all the application clusters, cluster 1, cluster 2, all the way up to cluster 1000. And we want traffic from these ingress to route into the individual applications in these clusters. And so traffic from here is going to go here. And since these ingress clusters are effectively replicas of each other created for global availability, they're all going to perform the same routing. Using ambient mesh to enable multi-cluster, we can set it up so that the regional ingress clusters can see all of the application clusters. But also importantly, we can set it up in such a way that that's asynchronous, and so the application clusters don't see the ingress clusters at all. Right? And this is one of the properties we have in our multi-cluster solution, is we don't have to allow clusters to have a fully bidirectional relationship. They can have unidirectional relationships. The advantage then with ambient mesh, because ambient mesh will automatically load balance and scale this traffic across multi-cluster backends, I can now have regional ingresses with full global load balancing across the entire application set. which is far better solution than, say, using DNS load balancing to say, well, I'm going to create public IP addresses for each at the edges of each of these clusters for each of the applications, and use a system like Route 53 or some other external DNS to say this application has to live at this IP at this point in time, and if it changes, let's say this cluster goes away, and I bring up Y over here, I have to publish an update to DNS, and that can take seconds or tens of seconds or even minutes to basically get distributed to all the potential public consumers on the internet. Whereas if I have a small number of these with public VIPs, those updates are almost instantaneous. So this is an example of a typical large-scale deployment of a hierarchical system. We're creating cluster dependencies to yield a really useful value in having a fully globally aware load-balanced ingress with regional failure modes, instead of using something like public DNS LB, which for building highly reliable ingress systems, right, this is a much better style solution. Other examples we see in the industry of examples where we do not want fully bidirectional relationships between clusters. Let's say one of the clusters that you have is for PCI compliance, and it handles all your payment processing system. Systems like that are very restricted in the dependencies they're allowed to have and the dependencies that other systems are allowed to have on them. And so if you can cordon them off into a cluster, then you can use the multi-cluster dependency management system to control what is allowed to talk to and what is allowed to make outbound calls to, making your system more auditable and therefore easier to reach PCI compliance. Another common example that we see is kind of dev, test, and prod solutions, where I want to have a dev cluster, and maybe that dev cluster can take some dependencies on some services in production, but nothing in production can ever take a dependency on a development system or a staging system. And so I can create these asymmetric dependencies that allow me to get those types of effects at a large scale and not just at the scale of an individual service. And so our multi-cluster solution not just handles massive scale, but because we allow for topological control, allows for more refinement in the architecture of your system, allowing you to achieve these kind of business goals. Visit ambientmesh.io to access free community resources.